Okay, types of bonding, virtual lesson, take 2. So I'm going to cover the 3 types of bonding, but first of all we'll start with a clever slide, an amusing slide, so feel free to pause it and try and work that one out. So we'll start with ionic bonding. So it happens between a metal and a non-metal. It involves the transfer of electrons from one atom to the other. This results in the creation of ions, which are then oppositely charged, and so they attract to each other, just like the north and south end of a magnet. They attract. So we have some examples of how that works. So here we have a sodium atom, 281, so it's in group 1 electron in the outer shell. It's got the same number of protons as it does electrons. So at the moment it's got a charge of 0. So there's the electron arrangement 281 at the bottom as well. You then lose an electron from the outer shell of the sodium, so that it becomes now something which is has lost an electron, so there's less of them, and so it becomes positively charged because you've got more protons. Remember, that's the change in chemistry, and you've got one less electron, so a positive charge of 1. The same, or an opposite thing will happen with a non-metal atom, like fluorine. So it has the same number of protons and electrons to start with, and so therefore has a charge of 0. It then gains a single electron, which goes onto its outer shell, so it has a full outer shell now. Now you'll notice that it has an extra electron than before, which means it now has more electrons than protons, so it has a charge of -1. And then its electron arrangement is 2,8, and I appreciate you probably can't see that down at the bottom there. What will happen then is that you end up forming a giant structure because the opposite charges attract, so that each positive metal ion will attract multiple negative ions, and vice versa. So you form this giant structure, and that keeps going in 3 dimensions until you form what is called basically a big crystal. So that's why salt cubes look the way they do. They look like a cube because they've literally formed by adding things on and on. Now we'll look at covalent bonding. So in this case, it's between a metal, a non-metal, and a non-metal, and it involves the sharing of electrons, not the transfer of electrons. So it does this so that each atom then has a full outer shell, because they always, when things react, they're doing it because they want to have a full outer shell. So in this case they're sharing to achieve that. And you can have various simple covalent compound molecules. So for example fluorine molecule F2 will look a bit like this with a shared pair there. So it's in group 7, it needs to gain 1 electron, so it only forms a single bond or a single pair of shared electrons with a fluorine atom, so that they now both have a full outer shell. You notice with the next example, chlorine here, is that we're using dots and crosses as we should be, as opposed to this one which really should have dots and crosses on it. And you get this overlap like in a Venn diagram, so this means that these 2 electrons belong to both the chlorine here on the right hand side and the chlorine on the left hand side at the same time. So Venn diagram is a place where they overlap. It means that it belongs to both groups, or it falls into both categories. So now the chlorine here has 8 electrons on that side, but also it has 8 electrons on the right hand side as well for this chlorine. And the same thing happens with oxygen, except it's in group 6, so it must form, in order to get a full outer shell, 2 bonds instead of 1, so 2 shared pairs, so that now both oxygens have in their shells 8 electrons. And neon, the molecule by itself, it already has a full outer shell, so it doesn't need to bond. And we then talked about the changing the state of various substances. So I listed a few on the board, but we've got the example of water again. Now these bonds between the atoms, they're covalent bonds, they're very strong. It takes a lot of energy to break them. But the forces between these molecules, the intermolecular forces, are weak. So in order to change the state of water, all you have to do is overcome these relatively weak forces here to force these, to move these molecules away from each other, to turn them into a gas. so it doesn't take much energy. The longer these molecules are, the more of these forces there are, these intermolecular forces. So the total force tends to build up when the chain gets longer, or the length of the molecule gets longer. So you do need more and more energy to overcome those forces. So the boiling point will go up if these molecules become longer. So it won't be water, but it can be, for example, we'll go back to that one. It can be, for example, the longer chain hydrocarbons from C1, as they got longer, then the boiling point went up because you've simply got more of these weak forces adding up to give a larger total force. You can have a second type of bonding with covalent bonding, and that's to form giant structures. So in a giant covalent structure, we've got three real main examples. I'm going to go through two of them, and you can feel free to look up silica or silicon dioxide as you wish. So diamond, you've got every carbon has all four of its electrons involved in bonding. So one of them is involved in here with another carbon, so one pair, one involved in this pair, one involved in that pair, one involved in that pair. So it's in group 4, all 4 electrons are then used up in these bonds, and it continues on again for a long time. So you form a giant structure with lots of strong covalent bonds, each carbon bonded 4 times. Makes it very hard. It also means that in order to change it from a solid to a liquid, you have to put in a lot of energy to break these bonds. All of them must be broken, so it means it has a very high melting point. And because it has no free electrons, it does not conduct electricity. Graphite, which is another form of carbon, an allotrope carbon, has only 3 of its electrons from each carbon involved in those bonds. So instead of having 4 bonds, it has 3, which means it's got that single lone electron from each carbon is then free to move between the layers, between these sheets of graphite, or these sheets, individual sheets of graphene sheet you may have heard about in the news. Those layers are able to slide over each other because the forces between are very weak. So you've got something which is soft and slippery but can conduct electricity, which has its own applications. And the last type of bonding then is metallic bonding, and that's between a metal and a metal. It forms positive metal ions, and they donate their outer shell electrons to a sea of electrons which move through the structure. So you have positive ions with electrons between those ions which hold them together by strong electrostatic attractions. It results in some properties. So having a pure metal, as we talked about in C1, then you've got a regular arrangement, so those layers can easily slide over each other, making it malleable and ductile and quite soft. And in between those layers, like I talked about, you've got basically positive ions with a sea of negative electrons. Illustrated here, but there's also another bit here as well. So, means it can conduct electricity very well, carries current well, and it also conducts heat very well. So that wraps up that lesson.